Thank you for joining us today for this Microsoft Reactor webinar. Today we'll be talking about how to take your machine learning model, pipeline, etc., and put it onto the cloud. After all the hard work, now is the time that we can actually make this productionized and ready, and make it available for other people, like customers, for other users. So it is a very exciting and useful stuff we'll be covering. So before we officially get started, just a few housekeeping items. Today we will be running code in Jupyter Notebook, and you're free to use your local version, or you can use the Microsoft Azure notebooks. This is essentially like a hosted version of the Jupyter Notebook server. If you're already a data scientist, or if you've already been working on projects, you probably don't need this. But for those who are new, this is a very useful tool because it bypasses all the setup and just makes things much easier. So what you have to do is look for this Azure notebooks and get started with making an account. So I'll put that in the chat. So you will need an account for that. Another one is Azure ML Studio. So this is the URL, and you will also need an account for that. Based on my latest knowledge, the last time I did this, both were free and did not require a credit card to sign up, and it's pretty nice to use. So feel free to get that started. So back to the slides. I guess I should introduce myself. So my name is Maddie Shang. I am currently a researcher and ML engineer. I'm working on some open source federated learning research, and that work is funded by PyTorch and Facebook. It's with a community called OpenMind. I'm also the Global Leadership Fellow for Machine Learning at Women Who Code. And other than that, I like to fly airplanes and do dangerous things like that for fun. That's a little bit of information about me. So going back to the slides, today the layout of the workshop will be, talking about slides, talking about things from a high level theoretical, conceptual level. And this is also a really good time for those of you who are interested in following along to set up your accounts and listen while you're getting all that sorted. I highly actually recommend everyone setting up the accounts either locally or just logging in, getting everything organized that way so you can run the code, right? It is much better learning experience, and you'll remember much more. So feel free to do that. So we'll talk about, we'll be going through some slides and talking about the high level, big picture kind of things, and then we'll switch directly back into the code, where I'll show you how to hook up your notebook to a more powerful machine that will allow you to do experimentations and train your models, etc. And we'll go through all the steps of data exploration, feature engineering, all that jazz. We will train and test split our data so we can have valid and accurate understanding of how well or not well models are performing. Well, we will use a decision tree based model to do this prediction, and after that, I'll show you probably the most important part is how do you turn whatever you just did, your awesome model, into an API that other people can use to call and get predictions from. We'll show you how to do that from within the notebook, but also from just straight up normal API call, right? So that's kind of the stuff we'll end up doing, and let's get ourselves started. So cloud-based machine learning, right? We're going to create a web services with Azure Machine Learning Studio. So at this point, some of you may have joined us for previous webinars, and I want to kind of get back to the big picture a little bit. So this is actually typically what a data science pipeline looks like, right? You have essentially the steps of having a business problem with some kind of requirements, and then you find the data that may be helpful in solving that problem or improving business value. You do some data cleaning, data engineering, data understanding. You prepare data after you figure out what kind of features might be useful, and then you feed that into a model. And over here, you will see an arrow going backwards because the steps of doing feature engineering and feeding into a model and doing evaluation and maybe starting all the way from the beginning is actually a very iterative process. When people say pipeline, yes, the data kind of flows in one way, but the process of doing data science is very iterative in actual practice, right? And then after you have a model you're pretty happy with, you evaluate it a few times, maybe you did parameter tuning, you're finally ready to deploy, right? The deployment step is actually where most people start to think about cloud-based platforms and using an API or something like that. But what we have found in practice is that as far as you get to the data understanding step, everything after that little block can and may be beneficial to be put into some kind of like professional cloud computing platform. Now, there are definitely a variety of different like platforms you can use for machine learning specific pipelines and DevOps and serving models and training models, etc. And today we're just going to cover one of them, which is Azure ML Studio. But yeah, so with that out of the way, kind of a little bit of high level review, let us go back to our slides. Excuse the slide flipping. Okay, so why do people want to use cloud-based platforms for machine learning, right? Well, this is a quick and affordable and accessible way to, make very sophisticated machine learning available for like any kind of small company, any kind of startup, and this will basically reach more users, right? So what this allows you to do is deploy train and tune models for repeated use online and on edge devices. So if you were a startup, what you might do is like, oh, I have this problem I'm trying to solve. Oh, let me go find some data sets, either public or from my own resources that may be helpful. I'm going to build a few models. I'm going to iterate on the models. I'm going to tune the models. And once that model is ready, you're like, yay, problem solved. Like, I now have a $1 billion startup idea ready to go. Not exactly, because if people cannot use it, you cannot deliver value, and therefore you don't actually have a company, right? So what the cloud platforms allows you to do is essentially take care of all the nitty-gritty security, robustness, like the platform engineering, the DevOps engineering, all that stuff. That is taken care of. Yes, you do have to pay a small fee for this typically, right? But most of these platforms will have free trials, and the small piece of like the fee you pay in exchange for the value it provides is like debatable. But even in like settings where you have a larger company, unless you have your own dedicated DevOps team, unless you have a dedicated like data engineering team, like frequently it still makes sense to use a pre-baked cloud-based ML platform. So the other benefit is a lot of these platforms will come with pre-baked and sometimes pre-trained models, right? So in case you're doing something, image classification related, instead of like downloading a model, training yourself, or downloading a pre-trained model, doing the fine-tuning yourself, a lot of the times these models are already available in the cloud platforms. So it makes it very easy to quickly iterate and test ideas, right? If every company you try to build that had to do with ML required you to hire a data scientist, required you to have a tuned model, required you to have your own data engineering DevOps team, like very few companies would actually end up, having machine learning available in their products. And this is another reason why, like, even if you're capable of doing like very serious and like hardcore and difficult machine learning, sometimes it's a good idea just to try if your business idea is valid, or just to try some algorithms and get it out there first, right? It's a validation every step of the way. So we have a lot of different use cases where large enterprise companies or even like important organizations like hospitals and public healthcare, etc., are using Azure Cognitive Services for their machine learning needs. So Cincinnati's hospital is using Azure Cognitive Services for NLP, right? Natural language interactions. This is probably some kind of chatbot, except all of this is done using Azure ML Studio. So here is a cheat sheet, and this is probably like a very valuable slide to spend a little bit of time on, right? Here is essentially a list of all the easy to access algorithms that comes out of the box with Azure machine learning. And this is also a good opportunity for us, like the more nerdy data sciencey, like academic people, to review the different options we have and when we should use certain algorithms. So as you may remember, there's roughly like two major classes of, algorithms depending on the outcome you're trying to achieve, right? We in general have regression, and we also have classification. These are essentially the predominant supervised learning algorithms. So the question is, like, hey, how do I know if what I have is a classification kind of problem? And how do I know what I have is a regression kind of problem? And this question is important because it informs you what models you should be trying and what models you might want to test out, right? So the way I can answer this question for myself is that if I imagine a valid value for the thing I'm trying to predict, and I add a very small amount to that value, is it still a valid answer? So let's do this as an example, right? If I'm building some kind of regression model to predict, I don't know, income based on some like attributes about, a certain individual, right? the prediction might be $70,000 a year, right? And then so now here comes the next part. What if I added a small value to that? Is like $7,000 and like $70,000 and like $20 still a valid outcome? Well, to me, it's entirely possible that someone, that's what someone would make in a year. So yes, like this is a valid answer. And therefore, this would indicate to me that the problem I'm working with, the problem I'm trying to solve, is a regression problem. And therefore, I should look at this list, the list in the pink box, to be choosing my initial models that I want to use, right? So then let's think about what happens if you're doing classification. So one example of this, and this is a slightly tricky example, is what month of the year is the individual born in, right? The answers might be 1 for January, 12 for December, etc., right? So let's say the result for some individual came back to be 8, right? Cool. If I add like a small amount to that, maybe like 0.01, does the answer still make sense? So if an individual was born in like month 8.01, it actually doesn't really make a lot of sense, right? Because 8.01 is still like probably like the first day of August, so the answer is still August, still 8, right? I also don't really know what it means to be born like in month 8.01. Another more simpler example, just to help you build intuition, is like the example of like binary classification, right? So if the outcome is only possible to be either this or that, or if you only have like two choices, either yes or no, these are what we call binary classification problems. And then so a very common example will be like classification of images. Given an image, is there a cat somewhere in the photo, right? In that case, you either get a 0 for no, I don't think there's a cat in the photo, or 1, yeah, there is a cat in the photo. I don't know what it would mean actually if the answer came back to be like 1.02, right? Is there like more than one cat in the photo? That's clearly not what we're trying to answer here. So that would be another example where I'm like, yeah, I'm dealing with classification, because adding a very small value to a reasonable answer no longer makes any sense, right? So roughly, regression problems will have continuous outputs, and classification problems will have discrete outputs. These are typically membership, like is this item in a certain group? That kind of result. So within classification, we already talk about an example of binary classification. Is there a cat in the photo or not? There's also a different way of doing classification, and that is multi-class classification. So an example of this would be, instead of if there is a cat in the photo, I can ask, okay, what is the traffic light currently at, right? Is it green, is it red, or is it oh, I almost said blue, that's not a valid color. Is it green, is it red, or is it yellow, right? So as you can see, like there's more than one possible values, and that is a multi-class classification problem. Now you can actually convert a multi-class classification problem, should you want to, into a binary one, where you ask, is the light currently green? Is the light currently yellow? And if not, the light is probably currently red, right? So that's how you can convert between these algorithms. There's actually a few more different ones that are a little bit like less common. So one of them is essentially classification, but taken to the extreme. That's called anomaly detection. Anomaly detection typically, well, anomaly detection could also be called outlier detection in a lot of cases, right? Anomaly detection is typically applied to a kind of a classification kind of problem. So a good example of this would be predicting out of all the transactions in a financial company, which ones are fraudulent. Or another example would be, given like, time series data, predict when the earthquake would happen, right? The reason these are like, problems that sound a lot like classification is this transaction fraudulent? You're like, well, that sounds like the binary classification problem that Maddie was just talking about, and you will be correct. The only difference between this and if there's a cat in the photo is that the probability of any given transaction being a fraudulent one is actually very, very rare. It's actually under 1% of the time, right? And because it's so rare, because the thing you're interested in is very like infrequently occurring in nature, this makes this kind of problem anomaly detection or outlier detection. Same thing for earthquakes, right? Most of the time, most of the places, there's actually no earthquakes. So if you were to draw out the history of like time, for example, and you were to try to pinpoint when there were actually earthquakes occurring, you will see that that's almost like pretty much never, right? So once again, these are problems that are more anomaly detection instead of like classification. Another way of doing, like something similar, but for a regression problem is called outlier detection, right? So let's say I'm trying to build a model to monitor if like a really tall human shows up, somewhere like in my vicinity. I don't know why I want to do that, but maybe for some reason I wanted to do that. So then how do you know if something is like kind of like abnormal, right? This only happens if, let's say, a person is like 3 or more standard deviations taller than what you would normally expect. So let's say like 8-foot human showed up, I would be like, okay, that is like very rare. It's very like unexpected to see in the natural population of humans, and therefore that is a anomaly. And once again, these problems share the similarity, no matter if you're doing regression or classification, that the thing you're interested in is naturally infrequently occurring or very rare in nature. So the last class of algorithm is clustering. And clustering kind of here denotes a much bigger class of machine learning, which we don't typically talk about a lot, and that is like unsupervised learning, right? So far, regression, classification, multi-class or binary, and anomaly detection are supervised problems. And they're supervised because for a large set of the data you're going to use for training, there is actually labeled data. As in, if I'm asking you to, hey, take this data and train a model and predict if a transaction is fraudulent, you already have a large data set where okay, this transaction is fraudulent, this one is not, right? If I were to ask you to predict the income of individuals, I probably already gave you a data set of like individuals and their income. And given an unknown individual, where you know a bunch of attributes except for the income, you're able to learn the patterns on your training data and then make that prediction, right? But sometimes you don't have that liberty. Sometimes you don't have labeled data. And in that case, that becomes an unsupervised learning problem. And clustering is a very key example. So what this would actually look like is, like I have a bunch of like scatter dots, right? There is some kind of y-axis, there's some kind of x-axis. I want you to tell me how many natural occurring groups are in this data. And in a real world example, this may frequently look like market segmentation for your customers, right? Or cohort analysis. So let's say you're a small company, you're a startup, you are getting some signups, you're getting some customers, already exciting, and you're like, hey, like who should we focus on out of our different users, right? We clearly cannot have the resources to make everyone happy all the time. So who should we really focus on? And then what you can do is take all the customer information that hopefully you're storing securely and you receive with permission, and you told them you're going to do this with this data. And then you run run a clustering algorithm, maybe k-means. And then what this will tell you is that, oh yeah, there's probably like 6 or maybe 4 different clusters, and this group is the biggest. And the commonality of this group will be maybe they're all female consumers tend to like your product better, or maybe these are people that tend to be online during these times, right? You can imagine the different examples. So with that said, you can use this little cheat sheet to help you in the early stages of you doing your like essentially model selection. This tells you what you might want to try. So here is another example of a cloud-based architecture with machine learning, and this is a real example based on manufacturing, right? So in manufacturing, a lot of times you have sensors embedded in your machines, and these sensors will be sending telemetry data, and these typically are like some kind of data stream. And you can actually send out telemetry data into a Azure ML based service called telemetry, not surprisingly. And then what happens is this data can be then sent into an events hub. So events are essentially slightly more filtered or modified raw data of telemetry, right? And based on the events data in the events hub, you can then feed that into a Azure Stream Analytics, real-time analytics, right? So this typically gets fed into some kind of like data analysis or some kind of dashboard at the end, right? So let's imagine what you might expect to see on these dashboards. Maybe it's how much products you're producing on that line every day. You would expect that to go up and down a little bit, but be relatively steady. You might also see things like temperature of machines or how many defects are being like generated at the QA stage, right? All of these things will tell you in real time, hey, something is going wrong, or some things are like less than optimal, or things are going normal. Keeping this data would also allow you to do other things. For example, you can combine historical data with real-time streaming data to essentially do real-time predictions, right? For example, even if you have not identified an anomaly, your model could tell you, hey, the inputs are coming very differently and something might be going wrong. So you can actually predict problems into the future. So you have more time to address it instead of react to it, right? So all of this is doable and actually better accomplished in cloud-based architecture with machine learning, and you can do all of this with Microsoft products. So let's talk about Azure Machine Learning Studio, right? So hopefully at this point, everyone who's wanting to follow along has had the opportunity to create an account in Azure Machine Learning Studios. And what we're roughly going to do is, hopefully this part is done. And if you want more time, or if you need us to wait, or if you have questions about this, feel free to put it in the chat. When I see them, I'll address them. The next thing we're going to do is hook this up to our Jupyter Notebook instance. And the way we're going to do that is actually very easy. It's included in notebooks. You can actually just copy the keys, right? And then the next thing we'll do is, going back to the slides again, we're going to do some data exploration, right? Data exploration, data cleaning. Because this is more of a clean data set, mostly to demonstrate the process, we won't spend too much time in item 2, but in real life, that's like a very critical and very important step where real data scientists and machine learning people spend way more time than they would want to admit. And then part 3, after we have our cleaned up data set, we're going to send that into Azure Machine Learning Studio, because if your model is going to be there and you're wanting to use more powerful compute to train your data, then it makes sense for your data to be there instead of being sent locally. The next thing we're going to do is essentially create a model in Jupyter Notebook, deploy our model into Azure Machine Learning Studio, and then we're going to see an example of how to consume the API or how to call the API and get results using essentially like a API call, right? So ML Studio is good for rapid experimentation. If you set up a pipeline or experiment, you actually do a lot of interesting fancy things like this. And it's actually pretty nice to drag and drop, so feel free to use it. What we actually typically do here, if we're not using ML Studio, is some kind of grid search, right? You're running experiments on how different parameters affect each other. Maybe like you're running different experiments on model architecture, and in which case this makes it nice. It makes the processing of the data and how you want to post-process your data consistent, so it's easier to compare. This also has the ability of helping you organize and track your experiments, because I cannot tell you how many times I was running experiments, and because I did not keep good notes, I had to basically redo everything because I wasn't sure what corresponded with what. This is a real problem in machine learning and data science. So this is actually the end of the notes, or the end of the slides. So then let's go straight into the notebooks. What we're going to do here is that we're going to make an account, and I assume that people have. And we can essentially get access to our credentials. Maybe I don't want to do that. Let me actually try a slightly different thing. So I'm going to stop sharing my screen for a sec until I have logged in. This is what it looks like after you're able to log in. And so here you see your ID and all that jazz. What you actually need is the information here, right? So what you're going to need to do is copy your workspace ID and also your authorization token under settings and put that into your notebook here. So for those of you who are wondering how to get access to this notebook, I assume that you have set up a essentially a some kind of Azure Notebooks account, and then what you can do is go to see all, and then use the GitHub repo of Microsoft Reactors. So you can use the one here, and you can go ahead and follow that. So I will give you the URL to the repo. So how to find it from this repo is workshop resources, and here, and then data science 2. There you go. I will put that into the chat as well. So someone's asking, isn't the Azure ML Studio the previous version, and would you rather be using Azure ML services? Yes, actually both versions work very similarly. So whatever you learn today should be, easily transferable to Azure ML services. So once you get this notebook going, we can actually exit out this because I have set up my keys. So you can essentially just set up the repo here. You need to essentially set some IDs, so reactors 3, for example, and then you can click import, right? This process may take a while because it's cloning a repo and setting up a container. So after that, you should be able to go back to your projects, and you should be able to, basically see all your projects here. And then you can actually click on one of them and click run. And after that, you will basically have an environment that looks a lot like Jupyter Notebooks, and that is fine. So let me know if people would like more time. And if not, we can proceed. So if you're in need of more time to do the setup, just give me a shout and we can, hold up for you. If not, I'm gonna continue. And yeah, just feel free to put a message in the Q&A. Same thing, if you have any other questions, I'll answer them as I see them. So here, all we're doing is that just following the instructions, right? Going to this URL, grabbing the workspace setting, the workspace ID, and also the authorization tokens. So there's actually 2 here, but you typically only need 1. All I have to say is make sure you copy the whole string, because sometimes, like, if I try to double click on it, it doesn't actually give me the whole string. It will just stop after the plus, right? So you do want to copy the whole thing. So what I'm going to do is, after I have this set up, I'm going to try to execute the cell and see that it runs with no errors. Once this is able to run without errors, you're basically set up and good to go. So once again, post a message if you're having trouble with this. So maybe take a second to explain what Jupyter Notebook is for those of us who are maybe less familiar. This is essentially the bread and butter tool for data scientists. And its specialty is that it allows you to kind of like build a narrative around your data science. Usually when you're looking at code, there's a lot of like magic numbers, right? For example, like why is this 42? Why is this 8, etc., etc., etc. This allows you to both like experiment and present your results, and then explain your experiments, and then talk about the next set of experiments all in one, right? So these are code cells. They're essentially, executable Python code. The rest of this, the stuff that looks like, Markdown, is basically Markdown. So notice how this cell has the type Markdown, and this cell has the type code, right? You can execute a code cell by, basically clicking to the cell and clicking run. There are also a good number of like keyboard shortcuts. On Mac, I think it's Shift Enter that executes the code, so you don't have to click around so much with your mouse. Another thing to note is that there's like a IN or LN 9. So, and if I execute this code again, it's going to go to 10, right? That's actually your execution number. So the thing that you need to watch out for about Jupyter Notebook is that it actually maintains the variable names in memory. So whatever you executed first, that value will be cached in memory, and if you were to execute that again, it will just get overwritten, right? So because the execution, like it's possible to execute much later in the notebook, and then come back to here and execute this code, right? It actually doesn't follow the order in which you laid out your notebook. It follows the execution order. So if you're seeing weird behavior where things are just not working and you don't know why, chances are your internal memory might be corrupted. So what you can do is restart your kernel and then try again. A lot of times, like strange behavior and strange errors goes away when you do that, right? So just watch out for the execution number and also the order in which the code is laid out. They may not always be the same. So after that little ramble, okay, someone's saying they need more time. Okay, where to get that ID again? Good question. So if you go to Microsoft Azure ML Studio, you will be able to go to settings and get the ID. So once again, if you click on settings, you will see immediately on the first tab, here's your workspace ID. And if you go to the second tab by clicking on authorization tokens, you will see your authorization tokens. It looks exactly like the screenshot, like that I'm looking at here. So hopefully that answers your question. So that message was sent at 2:44. So I'm gonna hang out and then maybe like spend another 4 more minutes. Just give people a little more time. And for the rest of us who are waiting and not interested in executing the code along with the workshop, you can feel free to ask any questions or poke around the reactors repo and look at interesting things. Or yeah. So just a few more minutes. And I'll stop sharing my screen for a sec. I'll reshare once we're ready to move again. What you're able to see is that all the, essentially all the code, and you also see on my screen what the execution will look like, and that way you can follow along using this as well. And it works the same way if you're wanting to run this code in your Azure notebooks. You can just upload a GitHub repo and then do that. You can just like use my fork of it. At some point, I will make a new fork of the reactors repo after the reorganization is done. But for now, I think this is just the easiest way to go about it. I'm not seeing other people making a request for more time, so let me know if anyone else needs more time. Okay, so I think we'll move ahead. And if you need more time, just like put a message in the Q&A, and we can hold up a little bit more. Okay, so going back to the original plan programming, we are able to execute this cell, which means we're able to essentially generate a instance of the workspace. So this package Azure ML is comes pre-baked if you're using notebooks in Azure. This is potentially not installed if you're running this locally. So then what you have to do is basically do a pip install. So here's another trick. You can actually run installation and like terminal commands in your notebook by doing pip install something something something, right? So if you're running this locally, you might actually just say that, and this will install this into your current kernel. Right now I'm using kernel Python 2. So for example, I can do like I don't know, what is a good package to install here? I mean, we can try pandas. I'm sure this is already installed, but just so you see what this looks like. So we'll let that run for a bit. So yeah, it's basically saying, hey, I tried to install the thing you told me to install, but it's already done, right? Like everything's fine. Why are you making it install it again? So, but that's how you would use it if you had to install other like libraries. And this is nice because it doesn't take you away from your workflow. Like usually you would have to go to terminal, activate a Python environment, do the installation, but this just happens like right away. So yeah. Anyways, so then let's move on to the the very light and very essentially like stylized step of doing data exploration and data cleaning and feature engineering. So today we're going to be using a forest fire related data set. So what I'll do is I'll change this back to whatever I want it to be. What you will notice is that in this repo, you actually got a bunch of data along with the code as well. So if you were to go back a few steps and you go to data, so this is the notebook we're currently running, and on the same level in the repo, there is a data folder. And from the data folder, here's all the data sets we'll be using today. Right now, we're looking at the forest fire CSV, and later on you will have the opportunity to essentially go through the entire process, building a model, looking at the data, deploying the data and the model to a cloud-based API using the PIMA Indians diabetes dataset. This is actually very well known and like kind of a well-known dataset in machine learning data science. This basically asks you to predict out of a set of individuals who actually didn't end up with diabetes or not. Anyway, so back to the forest fire example. So I think this is like forest fires. Good. So I was able to essentially read in the CSV by using my local relative path, which, like I mentioned, is in the data folder and the forest fire CSV. And we're able to essentially use pandas, which is most commonly shorthanded to PD. I don't know exactly why, but this is just a data science standard. We're able to read that CSV and we're able to get a data frame. So this I think is actually pretty old school. I think this works too. There we go. So you will see that I have a bunch of commented out code because I'm now going to do the data engineering and feature engineering data exploration step of like trying to plot some graphs and see what relationship exists in data. And because there's quite a bit of data, this graph may take a bit of time to sort itself out. So that's why you see this star over here. This is just indicating that this cell is currently running and still trying to compute. Once again, if anyone has any questions, feel free to put it in the chat and I'll answer them as I see them. Taking a while. Okay, so here we have the graph that I was intending to show you, right? So when we're doing feature engineering and doing like, I don't know, data cleaning and like data exploration, a lot of times it's helpful to plot some relationships between the key variables and ask yourself, hey, like, what is this graph showing me and is this what I expected, right? So as a quick example of doing, data exploration, in this example, we're actually going to be not predicting how big how large the fire is, which is I think the typical use case when they were doing this research paper. We're actually going to use some of the other data to try to predict the temperature in this data set. So the first thing you want to do is actually like look at the data set and look at the data annotation, right? Here's the example of like where this data came from. It came from a research paper about predicting forest fires using meteorological data. So predicting forest fires based on weather. And this is published here. It was published in 2007, and these are researchers who basically got us access to the data that we're using, and that's why we're referencing them, and they were using this for some kind of like research paper. But for us, let's look at what the data contains for us. We see feature X and feature Y. These are actually related to geospatial coordinates. The next thing we have is months of the year. Once again, this is the same kind of encoding we're using for predicting which months you're born in. 1 stands for January, 12 for December. And the reason I want to do this is that sometimes you would have features that are encoding in text, right? For example, January, December, like August. That is actually much harder for your machine learning algorithm to understand. So typically it's a good practice when you're doing feature engineering and data cleaning to turn that into a number. Like a machine is very capable of understanding what 1 means and what 12 means. It doesn't really understand. It takes a lot more to understand, like, what is jamming? Is this a shorthand for January, etc., right? Same thing for day. Day of the week is 1 to 7. 1 starts on a Sunday, for example. And then here we have MC and DMC and DC and ISI. These are essentially forest fire specific indices. I'm not a forest fire expert. I'm sure if there was an expert on the webinar, they can tell you all about this. But we're actually not going to be using these indices today for the purpose of predicting temperature. So I will let you, do all the Googling you want. And then we have temperature. This is the target variable. This is the variable of interest, right? So, and then the last few things we have is like relative humidity. As you can imagine, like if there's a lot more humidity in the air, we would expect to have less fires and maybe maybe also higher temperatures. Usually when it's hot, it's also humid where I'm at, but this is just a guess. I'm not a weather expert either. And there's also rain, right? Well, I would expect rain to negatively affect both forest fire and also the temperature as well. Yep. So then, we have the last variable, which is area, and this is how much of the forest was burned, right? So in doing some like very light data exploration and feature engineering, we're gonna look at this graph. This is essentially a scatter plot with lines connecting the data points. So here are some data points related to temperature, and the question is like, what am I looking at, and does this match my expectations? The answer is kind of yes, because I would expect higher temperatures to be correlated with like a larger area burn if you're having a forest fire, right? It would be unreasonable to expect a major forest fire to break out in Antarctica in like sub-zero temperatures. It is also not surprising that a lot of data points are clustered around 0, right? The reason these are around 0 is that just because you have a high temperature doesn't mean you necessarily have like large area burn. You have actual forest fire. So even though the higher values, like the highest point we see here, does indicate a correlation between temperature and area, having a high temperature does not necessarily mean you have a forest fire. So this graph totally makes sense to me, and it doesn't surprise me. But sometimes you are very much surprised by your data, and that's actually good news, because that indicates a opportunity for amazing features you can use to feed into your model, or you were surprised because you were mistaken about something, and that's an opportunity for you to learn and update your own intuition, right? So after this very light step of doing data exploration, we can then go to the rest of the steps, which has to do with working on a model, deploying the data, and then deploying the model. So here, we're going to essentially import from Azure ML again, and we're going to import this data type IDs. What we're saying here is that, remember this WS, this stands for workspace, which is a instance of a workspace object from this this library we were just using. So I should actually uncomment this. But this doesn't matter because we already instantiated a workspace successfully. So with our authenticated workspace, there are some data sets associated with that workspace. And we're going to essentially call a function called add from data frame. So notice this df, which we have here, right? This df we've been looking at and plotting from, this is just the pandas data frame. So it makes sense if we're trying to add a data set, we can call add from data frame. And here's where we're using that essentially data type ID. This is just the CSV. And here the name, you can actually name this whatever you want, but I have to name it like something weird because I already have run this cell many times, and it's not gonna let me have a duplicated name for my data set, which is good practice. So if I change the 108 and I execute the cell, eventually it will hopefully say that I have succeeded in uploading my data set. But if I were to just do this, I already know this is going to generate an error because the first time I ran this code, I already uploaded the same data set, forest fire data with no numbers afterwards, into my workspace. And here you're seeing the warning, hey, duplicate found for the asset name, blah, 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 blah. So that is like how you know what kind of error you're making. So if I do 109, I still expect this to succeed, and there we go. The description actually doesn't really matter. The description you can have duplicates, which is why I haven't had to change anything here. So there we go. All right, so here's another thing we can do. We're looking for essentially all the data sets that are like user generated, aka all the data sets that I have uploaded. As you can see, I've tried to upload many different versions of the same data sets with different numbers. So I'm gonna pause for a second to see if people had any trouble with uploading data sets, and if not, we will continue. So please, put your questions or your request for more time to in the Q&A. So just checking the Q&A, I am not seeing any requests for more time, so we will continue as usual. So what we're doing here is that we're going to make a reference to our dataset, which is done by workspace.datasets, and the name of your dataset you're trying to use. So I'm just going to use the first one I uploaded. I could have easily said, I don't know, like dataset 5. That will basically do exactly the same thing. And based on that, there's a bunch of metadata that's available for us because this data set is now in Azure ML Studio. And here it would be a good opportunity to verify this data is actually what we expect, right? So for example, wind, I'm expecting the first value to be 6.7. Let's look at our original data set to make sure we're not making any silly mistakes. It is still 6.7. The rest of the data looks familiar. It is actually good practice to constantly check yourself and doubt yourself and do a lot of almost paranoid checks when you're doing data science, because it is much easier and much more okay of a mistake to notice, oh yeah, I'm actually using a slightly different data set. Maybe I did some kind of processing that I didn't want to keep, and that's the one I imported. Because if you were to use the wrong data set, for example, and make a silly mistake like that, the downstream ramifications are potentially very big. And you may get to a point of saying, hey, nothing is working the way I expected. Where did I go wrong? And now you have to take all the steps to go backwards and try to understand, oh yeah, if this data set wasn't the one I thought I was using, do the conclusions I'm making about, what kind of models work better, what kind of parameter tuning work better, do any of those still apply? And if you're not able to say, yeah, they definitively still apply, you would basically have to start over again, right? So instead of making large errors that you don't know when you made them and having to redo work and have to question yourself and be stressed down the road, let's just be a little bit paranoid as we go and constantly check, are things the way I would expect? This is also a really good way for new data scientists and ML people to build up your intuition, your data intuition, your ML intuition. So after we have verified the data set is kind of what we expected, we're actually going to essentially move on from the data processing or the data engineering step and the feature engineering. We're actually just going to do essentially the train test split of our data. We're getting this ready to feed into our model. So essentially what we're trying to do today is that we're selecting the features wind, rain, months, and I guess relative humidity, and we're trying to predict temperature. At this point, I'm going to do that paranoid thing and ask myself, does this make sense, right? Here are the two questions I need to ask myself. Do I believe wind will help me predict temperature? Do I believe rain will help me predict? Do I believe months will help me predict? Do I believe relative humidity would? And I think when we're looking at the data set, we kind of talk about the potential relationship between wind and temperature, rain and temperature, months and temperature, and etc., right? The only one we didn't talk about is months. But then I would expect, obviously, certain months of the year, depending on if you're in the northern or southern hemisphere, to be warmer than others. So this is definitely a good value to include. And then the next thing we have is test size. So what this does is that it's telling the train test split, which we're importing from model selection in sklearn, how much of the data I should allocate towards testing only, right? We're using sklearn because sklearn is essentially what I call the gateway drug library to machine learning. A lot of experienced practitioners or even beginners like to use sklearn because the interface and the API is extremely well designed. It's very easy to use, and they have extremely good documentation. You actually can learn a lot about machine learning by reading documentation of like sklearn. So from that, we're going to import train test split, which is the function we can call. We're going to pass in essentially our training data and our training labels, and we're going to say we want to keep around a quarter of the data for our testing purposes, and then we're setting a random state. At this point, you might be like, what is a random state and why do we care about it? So the answer is the way train test split actually works under the hood is that it's taking your data frame like this and it's essentially doing some kind of shuffling. So instead of having 0 ending up in the first row and 1 being the second, you may have a situation where 3 is first, and then 2 is next, and then you have 0, and then you have 4, right? So the order of these rows might be shuffled. And after the shuffling, what it's doing is that it's saying, hey, give me the first 25%. I'm gonna keep that away from the model, and I'm gonna use it for testing purposes only, right? Because there's randomness, and randomness in computers are actually like kind of fake. There's no true randomness in computer. It's always based on a random seed. This is actually a random seed. And because we're controlling what a random seed is, even though the behavior is slightly deterministic, it is more repeatable. What this allows you to do is that when you're essentially analyzing the result of your models, let's say maybe you're changing this parameter from 8 to 6, from like 6 to 9 to 2, etc., you are able to know with more certainty the changes in your accuracy, for example, going from 66 to 63 to like maybe 70, etc., are due to the changes you're making to the model. It's not because your train test split is splitting data randomly, and because one time you got a slightly more lucky testing set, and the other time you got a slightly less lucky testing set, that your performance is changing, right? This is basically making your experiments reproducible, which is very important step of doing science, and especially in data science. So the other question I wanted to ask about this data, and it's very important at this step, is if I'm trying to predict temperature, is anything here going to essentially be helping me cheat? There's actually 2 very common ways in which beginners accidentally end up helping their models cheat. One is not doing train test split, and the other is including features that actually tells you a lot about what the final result should be, right? So let's try to explain this using 2 real-life examples. Let's say tomorrow there's a very big test. Your teacher's giving you and your friends some like practice homework to prepare, right? But later on you found out your teacher gave your friend the exact copy of the test that was going to go down tomorrow morning, and your teacher gave you like a good set of exercises, but they were not exactly the same, right? In that case, a reasonable and fair bystander, and you might even say, hey, like what you did is not fair. And it is because you would expect the friend or the model that's seeing the actual like test data to perform better on the test data, right? So that's one way of cheating, and this is why training, testing, like splitting your data set into your training set and testing set is super important. Actually, there's another way of splitting data set if you're doing parameter tuning that is more recommended in industry, and that is doing a training set and like a tuning set. So one of these sets can be used for hyperparameter tuning, and the other one that like has never been seen by a model either for training or tuning hyperparameters is used for testing. So that's actually like an even safer way of doing your data split. You can achieve something similar by using k-fold cross-validation, but we won't get into that today. If you're curious, you can ask me about it later. So the other way of cheating, and this is actually like more harder to find, and leads to a lot of like very embarrassing results, especially for like people with less experience, is leaking data, right? So imagine if I'm trying to predict the temperature, and this looks like it's maybe Celsius, and I had another column called TF, and you're like, is that TensorFlow? No, it's not. It's just temperature in Fahrenheit, right? So if I give my algorithm the temperatures in Fahrenheit, and I ask it to predict the temperature in Celsius, that is basically also cheating, because it's going to quickly figure out, oh yeah, like I can just divide the other one by some ratio, add maybe a constant, and that would always give me the right result, right? But then in the real world, that's almost never like how you want to use your model, right? In the real world, you're expecting your model to essentially maybe take all this information plus potentially this fake column that I just made up called temperature in Fahrenheit, and it's going to try to rely too much on this. It will never look at the pattern existing in these columns that helps you predict temperature, right? But then in the real life, like if you already have the temperature in Fahrenheit, you probably will not be asking a machine learning model how to convert into Celsius, right? So that's another example of like accidentally helping your model cheat. If that did end up happening, let's say I did include the temperature in the other scale in my training data, what would happen is my results will be incredibly good. Like it would not be very low, it would probably be in the high 90s. And then if I'm, not careful, I might be like, oh, I'm awesome. This model is awesome. I totally cracked this problem. I can now deploy this into production, show it to my boss, and have users use it, right? But then you will quickly be surprised to find your model actually does not perform very well in the real life, and that's because you included columns that you should not have, right? So the two things to watch out for is that train test splitting your data, and also making sure you're not leaking any information about the label with your columns in your data. So then what we can do is actually do the cool part, right? Which is building the model. There's two things we need to import. One is the actual model we're going to use, and today we'll be using a decision tree regressor. So a lot of people tend to associate decision trees with classification, and that is definitely a more popular use case. But decision trees can also be used for regression, and in a minute I can explain to you how that actually works. There's also a metric we're going to need to import, and that is R2-score. So this is essentially R-squared, the common R-squared that we use to evaluate regression models in statistics. This is not the adjusted R-squared because it doesn't penalize you for having additional data features. Anyways, so the way you use sklearn is very simple. You import a model you want to use and you instantiate a copy of that. So in the default instantiation, we're just going to use default sklearn parameters, and we're just going to set the random state. Once again, this is for repeatability. The reason we need to do this is that decision tree is also an algorithm that relies on randomness, and therefore, because you're making random choices, you want to make sure it makes the random choices in a similar way. And the next thing we're going to do after we instantiate a copy of this model is that we're going to call fit. Most sklearn models will only have two APIs, and that is fit, and then later on predict. And this leads to the simplicity and the ease of use of this library, and this is why this library is super successful in data science. So we're making a model here, we're passing our training data, and we're going to essentially fit the model on this line. After we have this model fitted, we can then use the fitted model to do predict, and we're going to pass in our test set. And so what this becomes is essentially, based on what we learned, the patterns we learned based on the training data for, everything that might affect temperature, the relationship between wind and temperature, rain and temperature, area temperature, sorry, not area, but like day and month in temperature, for example. Based on the patterns we learned, what do we think is the actual temperature for data that we don't have labels for, right? And this is essentially what the algorithm thinks is the actual value. And what we're doing here is that we're saying, hey, I want you to compare against what the actual values are for the test set and what you thought it was, and then tell me how well we did, right? So I'm just going to run this out naively, and what you will get is that, okay, yeah, this is not that surprising. It's because I did not actually run this out. Okay, here we go. So it was extremely fast to fit. That's the first thing you'll notice about decision tree and this algorithm. And nextly, the next thing we'll notice that we got a prediction, and our prediction score for the test set is actually like 0.63. So this actually isn't a really good score, right? I wouldn't actually, deploy this into production. So the next cell is asking you to play around with this algorithm and see if you can get a better result. And at this point, what I would do is I would actually look up this algorithm in sklearn documentation. So as you can see, I mentioned before, sklearn has a lot of parameters you can set. But one of the benefits is that if you're a beginner, they actually set very reasonable and expert kind of informed defaults. So chances are, if you're not trying to mess around too much, and if you're not familiar with what these things do, just use the default value will likely get you pretty good results, right? But if you do know what you're doing, and if you're interested in playing around, or if you're trying to squeeze better performance out of your model, you can actually essentially play around with these variables as well, right? So for example, criterion, here are the different options, and the default is MSE. So what would happen if we use MAE, right? The process of experimentation is as simple as this. So if I wanted to change that from MSE to MAE, can I just do this instead? The answer is absolutely yes. And I wonder what this does to our model performance. Oh, so it looks like that actually made it worse. So we'll do MSE again. Or actually you can remove it, because if you're not saying anything, it's just using the default, right? So there's actually two things that could be happening here. Either your model is performing, badly on your testing set because it's overfitting and it's essentially learning to remember the data in the training set instead of learning useful patterns, or it is not performing well because your model is not powerful enough, and that is underfitting, right? So this is just like if I were to say to you, hey, I'm gonna drop you facing west on the equator, and I want you to walk in a straight line, but you're not allowed to make any turns, and your goal is to go to the North Pole. You would be right to say, hey, Maddie, I don't think that's possible, because if I'm facing west and I'm walking along the equator and I'm not allowed to make any turns, all I can end up doing is walking around the equator, right? And that is a case of like a model being underpowered. It doesn't have enough parameters to even learn meaningful relationships. And so what does it mean when a model is like overpowered or a model is like overfitting, right? What that means is that your model has like so much like parameters, is learning to pick at the random relationships and the non-informative relationships that's specific to your data and not useful as a general pattern. So example of this would be, let's say I'm running some kind of like criminal enterprise, and we're doing like small scale kind of crimes, and I wanted to go rob like a high school locker room for some reason, right? Maybe I'm just like really interested in like half-used deodorants or something. And then I give my newest team member the task of like, hey, here is a example of a combo lock, and I want you to figure out how to undo all the combo locks. This person goes away for a couple of days, come back, and is like, hey, Maddie, I solved it. The answer is 1, 1, 2, 2, 3, 3, always. And then at this point, you'd be like, no, there's something wrong there. So what happened there? That is a classical case of overfitting. So the data I give to this individual to build a model on is just that one combo lock, right? And of course, the answer 1, 1, 2, 2, 3, 3 will open that combo lock, but it doesn't mean it will work for all the other combo locks, right? So basically, the model has essentially learned specific patterns about the data instead of the general patterns of like it's always like a few turns clockwise, 1 turn counterclockwise, and a small half turn clockwise. Like that would be a more useful pattern to learn, right? So right now, I'm actually suspecting the model is overfitting because this data set is actually relatively simple, and I know decision tree regressors to be a very powerful model. So let's try some regularization, right? What you can see here is that some of these values, for example, mean sample split 2, these are like not regularized at all. What this actually means if you're reading documentation is like, if you have a node, the minimum number of items in that node for you to make a split is 2. This is almost like basically redundant, right? For example, if you have a node and the node only has like 1 item, you cannot split the node without actually splitting the item, right? So this is essentially one of those like variables again too. So let's try that, right? Let's try this, setting that to 6 and see what happens. So what about 8? Okay, yeah, so it seems like regularization is actually working. So what about 12? Okay, so what about if we do 20? Okay, that's doing pretty good. So basically, as you can see, there are like a lot of options and choices you can use, and then a lot of times you would hook these variables up into a essentially a hyperparameter tuning kind of apparatus, and typically what we call grid search, right? So another one you can use is called like grid search CV search. And there are definitely like more sophisticated ways of doing this, but we won't go too much into that. So for now, I'll just set it back to 6. Okay, so how do decision trees actually work, right? Let me actually quickly go back to the slides, look at this example real quick. So this is an example of using decision tree for classification, but let's say we're actually trying to modify this tree for prediction instead, right? Instead of saying like if a certain like I guess plant is or mushroom is poisonous or not, let's predict how poisonous this is, like how much time you have before you have to get to a hospital before you're definitely not gonna make it. So now notice how instead of saying poisonous versus edible, this became a like a real number line kind of prediction. It could be like level 10, poisonous, or it could be level 10.5 poisonous. Let's say I just invented like a mushroom, toxicity scale, right? Okay, so what would happen is you would still essentially build this decision tree, and how you will make the prediction is that, let's say, I had a value that ended up in the bottommost poisonous branch of the tree, right? After I learn this tree, I'm gonna have a new data point. I'm gonna say, hey, is this a large mushroom or small mushroom? Maybe the answer is it's not big. So then I will go towards the right side of the tree, and then I'm gonna ask, hey, is this a spotted mushroom or not spotted mushroom? And I'll say it is spotted. And then I'll ask, hey, are the spots really big or are the spots not big, right? And then I'll say, oh, the spots are actually very tiny. So then I'm gonna go to the the right side of the tree again, and therefore I'm gonna end up somewhere it's called poisonous. And instead of saying poisonous, what I'm gonna do is I'm gonna take the average level of toxicity of all the mushrooms that ended up in that bucket, and I'm gonna use that as my value for my regression problem for prediction. Maybe all the mushrooms in this bucket, because they're all poisonous and also very poisonous, they end up with a toxicity value of like 27.5 out of 30, right? Then 27.5 is actually my prediction if I had a new piece of data that also ended up in that bucket. So overall, this actually makes a lot of sense, right? So we just went over how to use decision trees for classification, but then also for prediction. So going back to this, feel free to play around with all the other variables in the sklearn documentation, but for now, I think we can move on. And here's the last part, right? You went through all the hard work of like cleaning your data, doing feature engineering, exploring your data, finding out the cool relationships. You build a model, you iterate it a couple of times, you test it on your test set, and now you're at a place where you're like, yeah, like this is good enough, right? So what you can do then is wrap that into a predictor function and deploy it. So once again, we will be importing services, which is essentially a module that comes out of the library here. And once again, we're using the same variables we declared before. Notice how we use the same variables to essentially generate an instance of the workspace, like so. And we're using the same information to essentially instantiate the ability to publish to the same workspace. Because obviously you don't want people to send random models, random data to your workspace. That's just going to get clogged up, and you may end up having security problems. So the other thing we need to do is essentially specify what kind of data types are we expecting for the variables, right? So when, that's a floating point, rank is a floating point. Notice how months is not a floating point because it's an integer, because these months are numbers representing actual categorical values, which is it January, is it February, etc., etc. And this is expected to return float, right? The predicted value that we see here is a float. The predicted value we'll see in a second is a float, because temperature is a float. And this is also why this confirms that we're working on a regression problem, just to connect the dots one more time. So the next thing we need to do is specify an actual function. Notice how we're taking in 4 input variables and basically using the exact same code, calling predict right here, right? So if I were to plot out what xtest looks like, right? Let's plot the first 3 lines. You will see that it's basically exactly the same thing. But if I wanted to just predict on 1 unit of the data, okay, so I think I need to do like essentially .index log. There we go. So this is what the first piece of data looks like, and therefore I should expect to have 4 variable for the input, so I can call predict on this 1 data point, correct? So here, this is just the mapping function that tells me what the feeding where, and over here we're already specifying what kind of types we're expecting. So based on that, we can actually essentially deploy the model, and then also get a bunch of assets back that we will need later to call the API. So let's run this code. This is also one of the cells that may take a bit of time to run, but this just got deployed. So then what we can do is say, hey, let's make a prediction, see if this actually works. So we're going to send in these values and make it tell us what the temperature should be based on the model we just trained. And notice that because you're deploying a trained version of the model, this is deploying the weights that you currently have. That's generating this level of accuracy right now. If you were to essentially train the model, make it fit better, and then redeploy, you'll be deploying a slightly different version that may lead to a different prediction. So first for our predictor services, this is the result we're getting back. And we know that this process has worked. So now at this point, you might be like, hey, this is nice and all, but like I'm still making prediction in Jupyter Notebook. And if I were to do that, I might as well just use the simpler version and just say regressor predict, whatever value I want to predict, right? That is true, but what we actually have now is an API that's serving your model, which means all the users and maybe the the like web app department of your company or your startup, your team can now use the same API and put it into their website or their mobile applications. And this is exactly the same way we can do to call the API. So this is just some like API calling old school libraries that helps with that. We're going to essentially form a query that we're going to make to the predictor service properly. And what we need to do is, okay, so we have one input we're trying to test. Here's the mapping of what these columns are. Here are the variable names, and here are the actual values. And if you want to predict another value, you would just say input 2, right? And make sure this is a properly formed dictionary, but we're not going to need to do that today. So I'll get rid of that. And then what we're doing is JSON encoding that data and then making that a header and making that API call. So let's see what happens. We get the same result back, not surprisingly, right? So the first time you do this, it may take a little while because predicting and even training the model here is almost instantaneous. And sometimes this may actually take a while to end up with the results back, and you might be like, oh, why is this so slow? It's because you're making an API call and you're waiting for the results to come back, and that's why this may take a little bit longer than you would actually expect for a simple model like this, right? So with that said, this is actually the end of our official planned content. There is an exercise here that I would highly encourage you to do. So like I mentioned, there's a dataset folder that you can have access to. And in the dataset folder, there's the Pima Indians diabetes dataset, right? So I would encourage you to essentially over here, replace this dataset and go through all the same steps, do your best with feature engineering, data exploration, data cleaning. After you have clean data, do your train test split, and then also send the data into your workspace instance, doing your train test split, working on a model, maybe try a different model, or if you want to continue with decision tree, I think this is actually a classification problem, so you might want to import classifier instead. And I'll show you the documentation for that in a bit. Play around with the parameters. Once you're happy with that, deploy a new instance. You will probably need to change the function, etc., but you should work the same way. And then you can test a prediction to see if an individual with certain characteristics are likely to have diabetes, and then verify that you can launch that API as a web service. And if you wanted to turn this into a web app, right? Idea is to say, hey, type in your biometric information and let us tell you if you're likely to get diabetes or not, or something like that, just as a study idea. So I would highly encourage you to get started with that. And if anyone has any questions about what we talked about, or data science and machine learning, etc., in real life in general, feel free to put that in the chat. I'm gonna hang around for another 5 minutes or so, and probably another for 2-3 minutes after that until there's no more questions. And if no one has any questions, then I'll have a little bit more time in our day. I'll give you that time back. So this being the end of the webinar, I hope everyone was able to learn some useful information. I hope people had fun, and I hope you attempt this exercise again for yourself. So I'm just taking a look at this data real quick. I'll point out some items that I see that you may need to look out for if you're going to attempt this exercise for yourself. I already pointed out a couple, and that is, for example, using the classifier instead of regressor. Yeah, so it looks like there's some data about individuals, whether they're pregnant, or how many pregnancies they've had. If their glucose level, their blood pressure, their skin sickness. I don't know what insulin is, but that's something that we can look up. And their body mass index, I would expect this to be correlated positively with diabetes. And this diabetes pedigree function and their age. So here are some items I would look into. I would look at the correlation between all of these variables and the outcome, because I'm a little bit worried that this may be leaking information, leaking data about the outcome, especially if I don't know how this is calculated. So one thing I noticed is that for the ones that have a 0, the score is pretty low, and for the ones that have like an outcome of 1, the score is pretty high, right? So that may be like one way of helping your model cheat a little bit. So I will look into that. Those are the things I will be careful with. And as for the model, if you wanted to, you can actually use the decision tree classifier instead. So notice how there's a decision tree regressor. If you go to sklearn.trees, there's also a decision tree classifier. So this is the one you should use if you're trying to predict the binary outcomes of whether someone has diabetes or not. So this is another case where you can use that test, right? If the outcome is like, 1, if I add the small value to it, like say 0.2, like does that make more sense? You either have diabetes or you don't. You can't really have like 1.02 diabetes. Therefore, this is a classification problem, and that's how, a way that you can figure out that you should be using classifier instead. So this is the end of the essentially the stuff I want to talk about. And yeah, just checking for questions again. Thanks for the workshop. How can you get back to, I guess, me if you have questions? Okay, so here's how you can find me. I am on GitHub, and actually in one of the links I sent you has my essentially profile information. So this is me on GitHub. You can, look at some of the repos. I mostly do machine learning and blockchain related items, so feel free to take a look. And here's how you can like reach out to me if you need to. Yeah. And if you enjoyed and learned from this experience, I recommend you submitting feedback, either positive or negative, through the link that the Reactor folks just shared. Like if this is good for you and this is like helping you learn and this is somewhat valuable, then positive feedback will likely lead to more of these sessions in the future. And as always, if there are anything that I can improve, I'm happy to know about it and happy to essentially make it better. Someone's asking me if I'm on LinkedIn. I'm not gonna publicly share my LinkedIn profile just because one, it's not exactly updated and I get a lot of like recruiter spam, so I'm gonna not do that. But if you're really determined, I'm sure you can find me on LinkedIn. Like all the information here will basically lead you to my LinkedIn profile. But yeah, I don't typically go on LinkedIn because honestly, it's just a lot of a lot of spam at this point. But yeah, like if you have any questions I can answer now, happy to help for sure. So I'll hang around for another maybe like 2 more minutes, and if there's no more questions, everyone can just have 20 minutes of their day back. Thank you again for joining me. I appreciate